So you got 3 graphs to go over tonight. The rest of it is kind of like general questions going over what we talked about today. So graphing sine and cosine. Totally new. But kind of like graphing parabolas, or graphing polynomials, or graphing rational functions. So thinking back to like chapters 1 and 2 and all the graphing we did. These graphs will shift just like any other graph. So they can shift left or right. They can shift up or down, depending on what's being added or subtracted from the equation. They can stretch. They can shrink. They can get wide. They can get narrow. So the graphs have a lot of characteristics of functions that you have graphed and that you're familiar with. So we're going to try and learn all of those over the next couple of days. There are really 4 different things that can happen to these graphs, and pretty much each day we'll go over one of those 4 pieces. Today's the easy day. Today we're going to do the stretching. The stretching is really easy to do with a graph. The shifting is a little harder. So we'll go over just a little bit of that today. Let's talk about these words up here. So we're going to look at sine first. Does everybody have a graph that looks like mine? Just Jacob and Connor. Nobody else's graph looks like mine. Okay, good, good. Whew. You should not have a hill and another hill next to it. These are waves. So this is called a sine wave. And if you think about a wave in the ocean, a wave goes up, it goes down, and then it gets more momentum to go up, and then go down, and go up, and then go down. So a wave in the ocean, it has that like up, down, up, down, up, down, up, down. This is true, yes. If you're on the edge at the beach. But if you're in the middle of the ocean on a cruise or in a boat, you have that nice like just rolling ocean of water. So up, down, up, down. When you look at the domain and we talk about our sine graph, not sure what's going on. There we go. So the domain for sine, for what we have graphed, is negative 2 pi to positive 2 pi. Can my graph go beyond negative 2 pi and positive 2 pi? Rebecca? Yeah, because we can spin around the circle. So think of the unit circle. Yes, we can go to 2 pi, but our angles go bigger than 2 pi. So Rebecca, what is the domain for sine? Right, negative infinity to positive infinity. Because I can spin around the circle a whole bunch of times. So it doesn't just have to stop at 2 pi or negative 2 pi. And that goes with any graph that we make. In most graphs, if we made a t-chart, we only go to negative 2 and positive 2. But we know it can go beyond. So Rebecca, how about the range? How high and how low does it go?
Negative 1 to 1.
Yeah.
Brackets.
Perfect. Negative 1 to 1. And she said in brackets. So the highest and lowest points, the max and the min values give us the range. Even and odd. We talked about even and odd with our graphs that we looked at in the pre-calc. The first 3 chapters were pre-calc. Emma, how do we know if a graph is even or odd?
The odd one is this one, and the even one is like the W shape.
Okay. Yes. What's special about them, though?
Oh, for odd it goes like past this, it goes through it, and then it goes even.
As original symmetry? That's what you meant, right? You were getting there.
Yeah.
So odd functions have original symmetry. What do even functions have? Y-axis symmetry. Which is pretty much what Emma meant. So she said this one is odd. It's odd because, yes, it goes through the origin. It does pass through the origin, but it doesn't have to be odd. It's also odd because the other or the opposite quadrants are reflections of each other over the origin. So my first quadrant reflects to the fourth quadrant, third quadrant, not fourth. My second quadrant reflects, and it's at the same location, but just a reflection into the fourth quadrant. So this is an odd graph. It has original symmetry. And then two other questions on that side of the board over there. Max and min. So I know by looking at this graph that the max is right here and the min is right here. From 0 to 2 pi. And I'm only using 0 to 2 pi because that's our standard rotation around the unit circle. We always start at the angle of 0, we rotate all the way around, and we end at 2 pi. So where is the max located? How can I write that max as an ordered pair? So Connor, what would be the ordered pair for the maximum point? Yeah, at pi over 2, the maximum value of sine is 1. Because pi over 2 is 90 degrees on the unit circle. And that's when the sine value has its highest value at 90 degrees. So the angle of pi over 2, 1, is our max. Connor, where's the min then? Excellent. 3 pi over 2 and negative 1. Which is underneath on the unit circle. That's a 270. So the max is at the top of the unit circle, and the min is at the bottom. Now we're just thinking about it more as a wave instead of as a circle going around the circle. It's kind of like we're pulling that circle apart and splitting it apart. Any questions on those? How do we do on those? Okay, maybe. Amazing. The other questions, you may have had to refer to Google or your book to find out what they were asking about. The amplitude, it did give you a little formula, so you probably could have calculated the amplitude. What's the formula for amplitude? What does it say there, Jacob? So max minus min over 2. So if you calculate that, Jacob, what do you get for the sine? 1, yeah, because the max is 1, minus the min, which is negative 1. So that's really 2 divided by 2, so you get a 1. Does anybody know what the amplitude actually is, though? Jacob? Yeah, I feel like you should just teach today, huh? Yeah. No? So the amplitude is how high the wave goes up or how low the wave goes down. It's called the vertical stretch of the graph. In a parabola, we don't call it an amplitude, but a parabola still stretches. It just doesn't get a fancy name. Trig functions get names with all the pieces of them. So the amplitude is the vertical stretch of the graph. How high is it going to get to the max? And it's a distance. So it's always a positive, which is why the absolute value is around that. A positive distance, I go to the top, or a positive distance, I go to the bottom. So that would be a 1. Anybody know what the period of a graph would be? Of a trig graph? Anybody write a number down? What did you write down, Maya? Why would you write 2 pi? It's totally right, but why would we write 2 pi? How's that related to anything we've been doing, Ellie?
Okay, well, Maya told me it was because how far apart the 2 peaks are.
It is how far apart the 2 peaks are. What else is it with relation to what we've been working with, Rebecca?
Like a full cycle.
It's a full cycle around the circle. Now it's all coming back, right? Or coming to you.
I just read it in the book.
Oh, good. So a period is 1 spin, 1 rotation, 1 cycle, 1 turn, whatever words you want to use, around the circle. So yes, it's from the distance from kind of where I start to where I stop. I start at 0 on the unit circle. 1 full way around is 2 pi. So that distance from the stretch of the graph is called the period, 1 rotation around the circle. So there's actually 2 here because I have a negative part, which means I would go clockwise around the unit circle. That's 1 spin. And then we have the positive part. So this distance here are 2 sections of the graph. Pretty much once you have a repeat of the graph, then you started a new period or a new cycle or a new rotation. X-intercepts and y-intercepts, we know what they are. Abby, what would be an x-intercept? How do we define an x-intercept? Yeah, so just looking at the positive part, Abby, where does it cross the x-axis? So I heard pi, and 0, and 0, 0. pi 0. And then one more place, Abby.
2 pi 0.
Yeah, 2 pi 0. Those are the places where it's crossing the x-axis, the 3 angles that are x-intercepts. So I have 5 little arrows pointing over there right now. Those 5 arrows, why would I think they're important? Those are the ones that we're going to be focusing on graphing, yeah. So we're not going to graph all of them. But anytime you graph an equation, think of pre-calc. The equations that we graphed, did we find x-intercepts? By factoring, by long division, by synthetic division. We graphed x-intercepts. We graphed max and mins. How did we find max and mins? With the calculator. So we can graph max and mins without a calculator with Sine, because we're going to be able to graph those. But when we graph equations, we're going to graph 5 pieces. So in this case, x-intercepts, max, and min. So really there's 3 things we look for when we're graphing. We don't necessarily need the points in between if we know what happens with the curve. Y-intercept on this graph would be at 0, 0 as well. These markers I just brought a brand new one out. I don't know what happened to it. Oh, maybe this one's it. Y-intercept is at 0, 0 as well. 2 other terms. And Rebecca, did you read the book about that S word there? Couldn't find the S word. Does anybody know how to say the S word? I feel like it must be a swear word since I'm calling it the S word. So S-I-N we pronounce as sinusoidal. So O-I has that oi sound. A sine function. Yeah, sinusoidal. So the sinusoidal axis is the horizontal line. It's kind of like an imaginary line that cuts the graph in half. So think of the axis of symmetry is a vertical line that cuts a parabola in half. The sinusoidal axis is a horizontal line that splits the graph in half. So if it's a horizontal line, is it in y equals or in x equals form, Jacob? Y equals. And where is that horizontal line cutting the graph in half? Y equals 0. So I should have half the graph above, which means I have a curve, a whole curve above, and a whole curve below the line. That graph, that line will shift. It's not always going to be the same. And that's how my graph then starts moving up or down because of that line changing. Oh, perfect. Good. And then the last part is the frequency, and that's pretty much how often something happens. And it told you to just take 1 and over the period of 2 pi, so my frequency would be 1 over 2 pi. So when you talk about like the frequency of something spinning, you might say 1 out of every 60 seconds a bicycle wheel spins. Then it's really spinning slowly. You're biking really slow up a hill maybe. But the frequency of our graph, it repeats every 2 pi times. After I pass 2 pi, the graph is going to have that same repetition up, down, up, down. So the last thing before we move on to cosine, the 5 key points. We will be graphing 5 points for every single graph. You'll be asked tonight to label 5 key points or to list 5 key points. The y values are special because it's where our intercepts or our max and min occur. Those x values, 0, pi over 2, pi, 3 pi over 2, 2 pi, are also special because, well, it's where the x and y value occur.
Just a question for the frequency.
Yeah.
Do you want us to rationalize that?
No. Nope. Just keep it like that. 1 over 2 pi. So the angles that are up here are all the quadrant angles. So pi over 2 is called a quadrant angle because it's dividing the first and second quadrant in half. That's also where the maximum value occurs. So we won't graph the inside angles, the angles that fall within the quadrants. We'll just be graphing those angles that divide the quadrants. So how many quadrants do we have? 4. 5 points make 4 quadrants. They're going to be 4 sections of the graph that we focus on looking at. So 5 points create really 4 sections. What do I take to go from the starting to the peak to another x-intercept, an x-intercept to the min, and then my last section of the graph. So we'll kind of be thinking about it in fourths as well, 4 different sections to each graph. So we're going to go through cosine, but a lot quicker. Are there questions on sine? Good. So then looking at the cosine graph, I'll keep those hidden for a minute. Quinn, what do you think the domain of cosine is? Yeah, just because it changes from sine to cosine doesn't mean I have to restrict the angle. It can still go on forever. And Quinn, the range is? Yeah, -1. So that does not change. If I look at the graph, range lowest to highest point. Emma, is the sine, or I'm sorry, is the cosine even or odd? Because it has y-axis symmetry. So the y-axis cuts it in half. You can see this is a mirror image of the two. So I have the positive graph and then the graph for the negative x-axis as well. So that y-axis splits it right in half, so it's an even graph. Maya, what would the x? What is it? Oh, max. What's the max? Yeah, so the max is at 0, 1. Is there another max then? Where else? Where does the graph end on the right side? 2 pi 1. So in one spin around the unit circle, starting at 0 and ending at 2 pi, my cosine graph hits the max twice. Cosine starts high and ends high, or sine starts in the middle and ends in the middle. So cosine graph starts at its max and ends at the max. And then Maya, what's the minimum? The minimum occurs directly in the middle of those two maxes. That's why I have the lowest point of the curve. It's very evenly kind of grouped off. So the minimum is the middle of this graph for cosine. So cosine kind of looks like, two of them look like a, like stretched out W. One of them is kind of like a V shape, cursive V. You guys have to be right. Do you have to write cursive when you were in 2nd grade still? 3rd grade, 3rd grade. So kind of like that cursive V stretched out. All right, so amplitude here. If we have sine, the amplitude was 1. Kevin, if we have cosine, does the amplitude change at all? The stretch to get to the top of the graph? No. How about the period, Kevin? Does that change because we're dealing with cosine? No. Because I still start on the unit circle 0, and we still end at 2 pi. How about an x-intercept, Kevin? So at pi over 2, it's crossing the x-axis, and 3 pi over 2. So we can see, looking at sine versus cosine, they definitely have opposite x-intercepts, and they have opposite points that are max and min. So if it was an x-intercept in the one, it becomes a max or a min in the other one. And then Kevin, the last question here, dealing with intercepts, the y-intercept is? 0, 1. Happens to also be its max. Questions? Oh, because the standard way you go around the unit circle would be starting at 0 and going to 2 pi. So I'm just doing one rotation through the graph. Yes, we could list the other ones as well. I mean, we could list an infinite number, but just focusing on that positive rotation. One rotation around the graph. The last two questions, the sinusoidal axis is still at y equals 0. That's the middle of the graph that cuts the graph in half horizontally. It doesn't change just because it says cosine. So horizontally, I'm looking at the point where the line where half of it's above, half of it's below. And then the last part, the frequency, is still 1 over 2 pi. Because after I get to 2 pi, I have the same repeating graph. So it just starts high and ends up high. Questions on any of that general information? So you can kind of see like there are similarities. The differences are those key points. And I have those key points listed. So the key points for cosine starts at the max and ends at the max. So we have the angle of 0 and 2 pi, both having the max value. And then the other angles in between as well, we've got those intercepts and the min. but the 5 angles are the same. So I still have those 5 angles of 0, pi over 2, pi, 3 pi over 2, and 2 pi. It's just the y values are changing. And you see, they definitely have a pattern, like 1, 0, negative 1, 0, 1. So there's a pattern to those 5 key points. So we are going to do a nice, neat graph on the top of the next page. And we're just going to graph using the 5 key points. We're going to graph one for sine, one for cosine. And then we're going to see if we can talk about the amplitude and try and apply the amplitude to stretching or changing the stretch of this graph vertically. Questions? So if you flip the page, this first section is actually, there's a lot of stuff in the first section. So not only can we graph, but we can then write equations for graphs. We can do some applications of graphs. So there's a lot going on with graphs, just like we would graph in regular pre-calc. We can do all the same stuff in trig. So we're going to graph this. Can anybody list the 5 key points without flipping the page? So for sine, sine starts at 0, 0. Because at the angle of 0, the sine is 0. That's what that's really saying. Angle 0, the sine is 0 because I'm at the angle 0 in the unit circle. What's the next point, Kevin? Pi over 2 and 1. Pi over 2 is at the top of the unit circle. The sine is 1 at the top of the unit circle. Ellie, what's the third point? Yeah, pi 0. Because now we're over here in the unit circle. Sine is back at 0. Sine is the y. How about a fourth point? Ellie? 3 pi over 2. So close. Negative 1, yeah. Again, now thinking down on the unit circle, or down at the bottom. The sign is negative 1. And then all the way back at 2 pi, and we're at 0. So those will be listing 5 key points. That's all you have to do. Yes, they're going to change. Today we'll change y, tomorrow we'll change x. And then we'll start moving. When you graph this, you'll be asked to label the graph, and we're going to label it the same way that we did before. Each little box is going to represent 30 degrees. So if my first angle is pi over 2, or 90 degrees, then I'm counting by 30 degrees each time. So we're not going to plot points in between there, but we're still going to go over 3 spaces and put a little box, or a little tick mark at that box. And then I'm going to just continue to place a couple more tick marks here. So over 3 more, and then I have pi over 3 more, 3 pi over 2, and then at the end we have 2 pi. So the directions will say to label the graph, you just have to have the positive side labeled. The negative side, just carry on your tick marks. So we have a place to kind of locate our angles. But you don't have to label the negative side unless you like to have both sides labeled. And then when we go to do the y-axis, it's pretty much up to you how much you want to count by. So if you want each box just to represent 1, you're going to have a squished graph. So give it a little more height, count up a couple of boxes. I'm just going to go up 3 again since we're using 3s. Might as well keep the 3s consistent. But that's up to you. So if you have a graph tonight that has like a negative 12 of a stretch, then you're going to have to make sure that you just count by 1 each time so that it fits on the graph. So the graph is labeled, plot your 5 points, and then see if you can graph the left side as well. So you're plotting the key points for sine. And when you connect them, make it as curved as possible. It should be a smooth wave. Remember, our waves go up and down, up and down, up and down. So this is called one rotation around the circle, one period of the graph. I'm going to do the same exact thing, making a second period that just goes over here. So then I have 2. It should look exactly the same. So I should have a hill and a valley, a hill and a valley. So the frequency is 1 over 2 pi because after I want a distance of 2 pi, it repeats the same exact graph. Where the other graphs that we would have done don't work like that. A parabola is a U. It doesn't ever repeat. It just goes up forever. So these graphs have that like repetition because they're waves that continue spinning around a circle, but now we're kind of thinking about them as going up and down, up and down. So we said odd because odd means original symmetry. So try and graph the cosine. Again, make yourself a nice graph. Make it look pretty neat because we're going to use the bottom to try and compare to the top to see this difference with the amplitude that we'll be creating. Notice the x values are the same because it's still the unit circle. It's still those quadrant angles of the unit circle. So x should not change. So Odette, when cosine is 0, the value is a pi over 2, 0 pi, 3 pi over 2, 0, and then 2 pi back at 1. So 1, 0, negative 1 is 0, and then back at 1. So it starts high and it just falls to the middle and then crawls its way back up. Again, try and do the same thing you have for sine. So make a cosine graph. You can label it the exact same way. When you're graphing cosine, try and make it as it's going to the top, curving, because it should be able to curve to continue on. So it's not like a parabola. It doesn't just go straight up and down. So as you're approaching that last point at 2 pi, try and make it curve to that last point, because it doesn't continue going up vertically. It would curve and go down again. So try your best to make these curved graphs, because they do not have an end behavior that goes to infinity or negative infinity, because it just curves and goes back down. So Friday, you think you can graph these in 5 minutes, knowing the 5 key points to shape the graph?
Yeah.
Probably could do it tomorrow too, right? Sure. No. Yes. Taylor says, why not? Sure.
I can do it.
I'm game. Right?
Yeah.
Sure, she's learned a lot about arguing too from Mr. King.
I was getting mad yesterday.
Sorry.
It's okay.
So the one thing that we're going to talk about today is the amplitude. The amplitude is that vertical stretch. And it is the A, the number that's going to be in front of sine or cosine. So maybe I have a 7 there, or a 3, or a 5. And it's going to be the number that's in front of sine or cosine. Nice. We've actually done amplitude before. We just didn't call it amplitude. Does anybody remember the standard form of a parabola? What was the standard form of a parabola?
A, and then in parentheses, x minus h, and then squared plus k.
Or, what was the other form we used? What do they both have in them?
X squared.
Well, yes, x squared.
Y equals.
They both have that A. And they have a y equals, yes. But that A part in the graph, what did that do to the graph? Stretched it, shrunk it. Sometimes it told it to flip down if it was negative. That's the same thing in front of sine and cosine. It's the same number. It just gets a fancy name. So it's called the amplitude. So if we're stretching something, are we affecting x or y? Y. So this is going to affect the y of the graph. So underneath here, it says A, which represents the amplitude, is really the absolute value of A, because you have to think of it as a distance. How far are you stretching? So it's when you're asked for the amplitude is actually the absolute value. The negative part just tells us the graph goes down. It just flips it. But the actual value of amplitude is the absolute value of it. Underneath, you will see that we do have a couple extra letters, like A, B, and C. The B is going to do something to our graph. The C is going to do something to our graph. And there's actually one more letter that we will add on. There's going to be a D in the back as well. Our parabolas didn't have a D. It just had the A, B, C. So there's going to be 4 letters. Each of those 4 letters do something different to the graph. So we'll talk about how those differences occur. If A is between 0 and 1, the graph squishes down. That happened with the parabola. If there was a 1/4 of the parabola, it was a vertical shrink. If the A is bigger than 1, then it stretches. I would have a steeper parabola because the A value is bigger than 1. So you have 2 graphs underneath, both cosine, if I can find them. Here we go. The one says y equals 1/2 cosine. So what's going to happen with that graph because of the 1/2? It's going to shrink. Because instead of going up to 1, we're doing half of that. It's going to shrink. And then the second one you have is 3 cosine x. And the 3 is going to make it stretch. So how does that change the y value then? How would I show that in my ordered pair? Go, Jen. Yeah, so our ordered pair is going to be the angle, and then the y value is going to be multiplied by a. That's how I actually get a vertical stretch of the graph. Whatever your a value is, gets tripled or gets cut in half. I'm sorry, whatever the y value is, gets tripled or cut in half. But a affects y, and the way it affects it is by multiplying. So I want you to list the 5 key points with the a value of 1/2. So my x shouldn't change because the x is the angle. The y is just changing because you're multiplying y by 1/2. See if you can list those 5 key points, and then we'll graph it, trying to see the difference. So our new point should be 0 and 1/2 instead of 0 and 1. So we're only stretching half as far as we would before. Yeah, it's cosine. So we're looking at a cosine graph. So we're starting up high at 1. I'm going to label the x-axis exactly the same way because x isn't changing. We'll talk about how that changes tomorrow. And I'm going to label the y-axis the same way because I want us to be able to see that change in the stretching of the graph. So I'm still going to count up 3 and call that 1. So make sure your points only go halfway. So you should see the shrink in the graph. It's being squished vertically. It doesn't go as high. So when you look at your graph above and you look at this one, you should visually be able to see that it isn't as high of a graph. The peaks aren't as high. And then the other one just says y equals 3 cosine x. Still cosine. So this one now should stretch because the y value is being tripled instead of it being half. It is a pattern. All patterns. All patterns. They're cyclical. Whatever that means. So when you graph the other function for cosine, this one is going to definitely stretch. Try your best when you're graphing it to still make it curved. So the tip of it should be curved as you're going down. All the way down. See a really long stretched W. So the graph paper that you have, again, you're only doing 3 graphs. You can place your key points right next to the graph. There's a little spot for you to put the problem number on there. You can put your key points. Make sure you label the x-axis. And then, like, I think I copied 1,000 pieces of graph paper. So then it's all the same special just for trade graph paper. Just for trade.